ions. Basically, what ions are is they are charged particles. Let's take a look here. We know in general that for a neutral atom, earlier I stated to you guys that for something to be neutral, the overall positives must equal the overall negatives, right? So we say that the number of protons, which are positive, equals the number of electrons, which are negative. All right, so we're going to use that to help us figure out what charges on particular atoms and elements should be. So it works out where the charge is equal to the number of protons minus the number of electrons. And I'm going to go ahead and put the little symbols there so you know what the charges should be. So in general, if you have a positive charge, which one is greater? The protons or electrons? Protons are greater. So we can say that the number of protons are greater than the number of electrons. And then you have the reverse case where if something is negative, that means that the number of protons is less than the number of electrons. It turns out, depending on their position on the table, we can actually use their position to help us kind of estimate, predict what charge they should have. It turns out that metals tend to form cations. That means they are positive. And then nonmetals tend to form anions. And if we're saying the word anion, we mean that it has a negative charge. So with that in mind, let's take a look at what happens here with lithium. And when I'm talking about metals, I like to put a little 0 here to say that it has no charge. It turns out that since lithium is a metal, it will tend to become lithium plus 1, and we get 1 electron. So metals lose electrons to become positive. All right, so we can go ahead and calculate how many different protons and electrons we should have based off the formula. So how do we figure out the number of protons in lithium? Atomic number, right? Periodic table. So here. So lithium has a 3 on it. So it tells me that it currently has 3 protons. And if it's neutral on this side, how many electrons did it have when it's in the metal form? Had 3, so they have to be equal. And then on this side, did the proton number change if we're still calling it lithium? Nope, if we're still calling it lithium, the proton count did not change, but how many electrons does it have now? 2. Yep. So if we're taking a look at the formula, the charge is equal to 3 minus 2, and always be clear on if it's positive or negative because it does matter. So this is a positive 1. So let's take a look at chlorine. So chlorine, let's just say that it's the atom chlorine. And which side of the table is chlorine on? Is it a metal or a non-metal? It's a non-metal, yes. So if it's a non-metal, the exact opposite is going to happen. So non-metals will gain electrons to become negative. So the way we show that is you put the electron on this side, and then these combine to make a Cl minus. So we can say that non-metals gain electrons to become negative. Notice here on both cases we're just talking about the shuffle of electrons. The protons are staying the same. Alright, so we can go ahead and figure out the same things here. So chlorine is element 17. So if it's neutral, we know that it has 17 electrons and 17 protons. We got the proton number based off the definition of it being element 17. Alright, and then if it gained 1 electron, the proton count stayed the same, but then we have 18 electrons there instead. So let's go ahead and take a look how these will go together. So when putting these together, and keep in mind that this naming part here that is technically chapter 5 if you're following along the book. So the way that we put these together is you arrange them in a ratio where that the overall charge is equal to 0. So if we have a +1 here and a -1, we essentially just need one of each, right? So LiCl. And this makes what's called a binary compound, meaning that it has two atoms, or atom types, involved. Another thing we can call this is a salt, or ionic compound. So if you have a compound that is a combination of cations and anions, you can go ahead and call it a salt. So it's a little bit different than the table salt that we eat, right? All right, in naming a binary compound, the way you name them is you just simply state the name of the metal. So the metal name as it reads on the periodic table. You then have the non-metal name. However, we give this the IDE suffix. So here we have a space. So metal name, non-metal name, but we give the IDE suffix. So the way we name this compound is lithium. And then we have chlorine there, so we're going to say chloride. Notice here we have the IDE ending. Let's take a look at sodium chloride. So we have Na, metal. It's just going to gain or lose electrons based on the position on the periodic table. So it's there on the left side. So they're going to gain or lose electrons. It's going to lose electrons. So it turns out that sodium does not like being in the metal form. It likes to be in the cation form. And it loses an electron to something else. And we can go ahead and do the same type of calculation here. We know that if it's neutral, there are 11 protons. And the electron count is the same if it's neutral. Here we have one less electron. And we did chloride earlier, didn't we? That was Cl minus. So when you put these together, we put them together in whole number ratios. It works out where we need one of each because one's a +1, the other one's a -1, so overall at 0 if we have one of each. To name this, you state the name of the cation or the metal, sodium, and then we have the chloride ending, very similar to what we had before. Does anybody know the common name for this particular salt?
Table salt?
Yeah, when people say the word salt, they're typically referring to specifically this one. So this is table salt. Keep in mind that when people use the word salt in chemistry, we are referring to compounds that are ionic. It's not just the table salt that you put on your French fries. It's anything that is ionic. So for example, I put salt into my water softener this weekend. Did I put sodium chloride? Probably not. It was probably potassium chloride. Let's compare sodium and lithium real quick and see if we can come up with some trends here. So do you notice anything similar between the two? They tend to make the same charge, didn't they? They're both become +1. And then if you take a look at the periodic table, where are they in relative position to each other? They're all in the same family, right? They're all alkali, or they're both alkali metals. So it turns out that we can actually use the group numbers to predict what the charges are going to be. We're going to go over this in a lot more detail, chapter 9, but for now I just wanted to point out that the way that these work is the metals and nonmetals will gain or lose electrons such that they have the same number of electrons as the closest noble gas. Meaning that elements on this side of the table, it's either for them to lose electrons to become like the noble gases. So for example, sodium had 11 originally, it lost 1, And then after it lost one, it had the same number of electrons as neon. And then lithium originally had 3. It lost 1 electron to become like helium. It then had 2. And we're going to see that with all of these different charges, they're going to end up like that, where they have the same number of electrons as whichever noble gas is closest. All right, so I'm going to go ahead and write common charges here on the table. Things that are in group 1 tend to be a +1. Based off the same logic I just mentioned here, what do you guys expect the second group to +2? All right. The ones in the middle, these transition metals, those are the weird guys. They like to do variable charges. So some of them will have common charges, but for the most part, we skip past those. The next ones I want you to be aware of are this group here. This group, they tend to be a -3. This next group, they tend to be a -2. And then the halogens tend to be a -1. I highly recommend committing that to memory. And by elements in the same column, because they have similar properties, will end up making similar types of ions. All right, so let's take a look at a different example. Let's take a look at magnesium and let's say sulfur. All right, so then I use the periodic table to determine what their charges are going to be. So magnesium, I find magnesium on the table. It is in this group. So I'm going to say it has a 2+. All right, notice the way I wrote the 2+ there. I am okay in class if you write it as +2 or 2+, but when you're doing the homework online, it's going to specifically look for 2+. If you write it as +2 on the online homework, it will mark you incorrect. Just keep that in mind. I know it's being picky about that, but technically, we put the number first. And then what about the sulfur? What should the charge on sulfur be? 2-, yeah. So right here, sulfur's in that group, so we write it as 2-. If one is a +2 and one is a -2, then how many of each do we need to balance it out to be 0? Just need one of each, right? Similar to the other ones. So the way I write this formula is MgS. All right, let's go ahead and name it now. So we name the cation first. So the metal name, magnesium. And then what should I call the second word here? Sulfide, yes. Calcium and chlorine. We did chlorine already, didn't we? Yeah, a couple times. So this one is a Cl-. Calcium, 2+. So when I put these together, notice how if I have just one of each, it's not going to quite line up, is it? So how many of the calcium should I have and how many of the chlorine should I have? Yep, so for it to balance, we need 1 calcium, 2 chlorines. So there's a couple ways to do this. I'm going to do it the longer way right now. So if you write it out, we need 2 of those so it balances out. And we end up with Ca, Cl, and then we have to put the subscript over here to tell us that there's 2 of them. The very convenient way to do this is the so-called cross method. You may notice here that this number went there and this number went here. That almost always works. So you just basically swap their numbers, their whatever power that's to, change it for a subscript. All right, and then let's go ahead and name this calcium. And notice here I'm just going to put the word chloride. And the reason why I didn't say how many chlorides there were in the name is because anybody can figure out that this is a Ca2+ and Cl- from the name. And then the person has to put together how many exactly there are of each.